My name is JIT10303 and my matric number is S25A0754. Introduction. In today's digital world, visual information is one of the way data is shared. Digital images are widely used in fields such as healthcare, security and satellite analysis. However, image captured by sensor often suffer from poor lighting, noise or low resolution, which reduce their quality. This is a serious issue because professionals like doctor, security agency and engineer rely on clear image for accurate decision. Clear image quality can lead to misdiagnosis or failure to identify security threats. Therefore, enhancing digital image using mathematical model is not a luxury, but a necessity.
Good morning, madam. My name is Josephine. The matric S25A0756. I will explain how computation, the mathematics matrix is applied in image binary adjustment. Each number in the matrix represents one pixel. For binary image, the value only includes 0 and 1. For grayscale image, the value is between 0 and 255. For a RGB image, the image has 3 layers, which are red, green, and blue. Next, we adjust the brightness using simple matrix addition. We represent the image as a matrix I, and we create a number k. To make the image brighter, we add the same number k to each pixel in the matrix. To make the image darker, we subtract k from each pixel in the matrix. Change all pixels at the same time. The brightness changes evenly across the whole image. This is faster and easier than changing pixels one by one. However, pixel value must stay between 0 and 255. If a value becomes larger than 255 and smaller than 0, we limit it to stay in that range. For RGB image, we do the same thing for the red, green, and blue layers. This makes the image brighter without changing the color too much. Finally, we use Python and NumPy to do this calculation quickly and correctly. So these projects show how simple matrix operation can solve a real image problem. Thank you.
My name is Computational. It is already my matrix number is S25A0710. But 3 problems without use of computing mathematics. Without computing mathematics, especially when it's techniques, image processing would not work efficiently in real life. Computers would need process image pixel by pixel, which is very slow. Example, the 4K image that normally take less than seconds would take several times making video applications like video calls. Live streaming is impossible. Secondly, basic image operation, which is rotating, resizing and moving the image, depend on metrics based on transformation. Without them, image would be low quality or becomes distorted. Thirdly, mathematics also essential for image like JPEG, which reduce file size while keeping good quality. Without compression, image would take up much storage and be slow to set online. In conclusion, mathematics is the foundation of modern image process. It's essential for fast, high quality or real-time application to use every day. Alright, that's all.
My name is Computational the matrix S250733. Today I will explain part 4 as we discussed in the part 2 the current method realized on simple scalar additions, which is a one-size-fits-all approach. The major problem is that it is context blind, it is brightness everything equally, often leading to the overpass, highlights and lost details. To overcome this, part 4 proposes an adaptive AI-driven matrix enhancement. Instead of just editing a number, we are introducing an intelligent system that understands the image contents before making any adjustment. Technically, we are operating the max in part 2. Use a simple 4i plus K formula in our new solution. We transition to a cranial correlation and tensor processing. We use a 3+3 matrix or kernel to scan the image. That allows the system to perform wedge calculation rather than the simple addition. By using a neural network tensors, we are processing RGB channels simultaneously, ensuring the mathematically relationship between the pieces remains intact. Compared to the basic method, the SI solution offers a massive leap in quality. First, it solves the clipping issue. While part 2 blinding passes pixel values past 255, our AI uses a dynamic scaling to brighten dark areas while preserving the highlights. Second, it maintains a color fidelity. In part 2, colors often shape our look, wash out. However, our proposed solution balances the color matrix to ensure the output look natural and professional. This isn't just a theoretical concept, it is highly realistic. Today's GPUs are specifically designed to handle these complex matrix multiplications in a milliseconds. This is the exact technology used in your smartphone night mode and in advanced medically X-ray imaging. We are moving from a manual basic calculation in a part 2 to a high-performance real-time application to a part 4. To summarize the progress from the part 2 to part 4, for the first one, max, we move from a simple addition to smart compilation multiplication. For the two, logic, we move from the global adjustments to the adaptive context of word processing. For the third is results, we move from the loss of detail to a detailed observation. In the short, part 2 is about changing numbers, but part 4 is about understanding image through a computational mathematics. This is why part 4 is a significantly more advanced and effective solution.
In conclusion, metrics play a big role in the digital world as they provide an efficient and accurate way to process large amount of data. In this project, metrics are used to represent and manipulate image data, enabling image to be enhanced, analyzed and improved effectively. Computational mathematics acts as the engine behind modern technologies such as smartphone, cameras, medical imaging system, and artificial intelligence. As we move further into the big data and AI, metric computation will remain essential in transforming raw data into meaningful information. Therefore, metric will continue to have a significant impact on current and future technology advancement. Thank you.